All right, go ahead, Ryan.
Okay, great. Thanks, Leslie. For everybody who wasn't familiar with partition point-to-point, we've presented this a few times now, so hopefully you get the basic gist of this. This is useful for basically chopping up existing MPI communication functions and basically letting them be done in smaller parts so that you can do things. The real goal here is that it provides some benefits to things like threading or tasking, this sort of thing, when you have multiple actors within a given MPI process that all want to access MPI. Partition point-to-point lets us do some interesting optimizations for these things, as well as providing a potentially lower overhead way for multiple execution contexts to interact with MPI. So this doesn't require the full thread multiple thing that you'd expect out of MPI. If you needed to use threads with it, there's some fairly lightweight atomics that you can use to lock all of these things down and just say basically parts come in, and MPI can optimize these things. So that's the basic gist of it. If you want a much more thorough overview, I did do a presentation from the last virtual meeting, which was recorded. If you'd like to review that. Now, we presented this in Chicago. I presented this in Chicago, and we got some feedback. And this is the version with all that feedback incorporated, plus a few other fixes that we had. So some of the feedback was we've touched up some of the examples. People wanted some, so I'll run through the list. We touched up some of the examples. There were a whole bunch of inline text changes and suggestions that we've hopefully gone through and addressed all of those now that people put on the ticket. So all those will be in the text that I'll be going through today. People mentioned that they wanted more clarity on the matching ordering of the init calls, and we've added that now. It aligns pretty well to how you did some of the starts in persistent communication and the same ordering that happens there. We've solved the non-blocking init call problem, and I will get into this in much more detail about how I think it is completely solved and whether people are not like this particular solution. I think it's a fairly elegant solution, but we'll talk about that in a little bit. There were some ordering issues on some of the functions. We fixed all of that up. There was some stuff on how we handled P-ready for the range and list calls. They've been clarified quite a bit. And they follow the same rules as the regular P-ready. So that's all been added into as text. We've clarified that partitions from the send side and the receive side from their numbers do not necessarily mean that they line up. So for example, if I have partition 4 from the send side, that doesn't mean that it has anything to do with partition 4 on the receive side. They are not necessarily equivalent, although they are allowed to be if you want them to. Partitioning on both sides can be independent, essentially. We've clarified that we're just using test and not using wait anymore. There was no point in having some overtaking rules that we had in there before, so we removed those. The test calls for multiple different tests, we've gone down to test any, because people said that they didn't see a lot of use cases for the sum and all, and we weren't quite sure exactly how we were going to do the API for them. Anyways, there was some discussion about this, so for now we've cut out the others that we don't have solid use cases for, and we've got any in there through there. And there's a whole bunch of other little tiny fixes that went into this chapter, but those are sort of the biggest, meatiest things that changed. There's not a lot of change to the introduction, so I'm just going to run through it really, really quick. So basically, the introduction refers back to Chapter 3 and explains what partitioning means. We reference back that this is known as fine points, so if people want to go back and look at all the functionality and why this works and how some optimizations happen, the actual research foundation is back, and it used to be called fine points. You can look it up that way. I'm going to we didn't really change much there, so I'm going to start in 4.2 where we started to change some stuff. So here, I'm just going to start reading, and people stop me if you have questions or you want to make comments throughout, or you want to bring up something in a different section that you really want to discuss. Stop me now, and we can jump there. Otherwise, I'll just start at the beginning. So Any major concerns? Fantastic. Okay, let's start with 4.2. So in this section, we've said the semantics of point-to-point partition point-to-point communication. So it says a valid MPI implementation guarantees certain general properties of partition point-to-point communication progress within point-to-point communication, which are described in this section. So persistent communications use opaque MPI request objects as described in section 3. So partition communication uses these same semantics. Partition communication provides fine-grained transfers on either or both sides of a send-receive operation described by requests. Persistent communication semantics are ideal for partition communication. They provide MPI p-send init and MPI p-receive init functions that allow partition communication setup to occur prior to message transfers. Unlike persistent point-to-point communications, partition communication initialization functions are non-local. But we'll get to that in a section, how they can be non-local, but they can also be non-blocking. The partition communication initialization includes inputs on the number of requested partitions on the sender and receiver side. Once an MPI p-send init call has been made, the user may start the operation with a call to a starting procedure and complete the operation with multiple p-ready calls equal to the requested number of send partitions, followed by a call to a completing procedure. We'll see later that this completing procedure is defined as one of the MPI test family. A call to MPI p-ready procedure notifies the MPI library that a portion of the data buffer is ready to be sent. Notification of partial completion on the receiver side can be done via fine-grained MPI p-test calls before a final MPI test on the request itself, representing overall operation completion. So I will clarify here for some people, this is where we're saying that you don't have to call MPI p-tests. You can do a fine-grained MPI p-test if you want, but you're not required to iterate through all the different individual partitions testing if they're complete. You can just call a final MPI test and be done with it. You don't actually have to test individual partition completions on the receiver side. So we say, likewise, for sender-side operations, notification of completion can be done via MPI test. A full set of methodologies for starting and completing partition communication is given in the following section. So we give some advice to users here. This hasn't changed. So having a large number of receive-side partitions can increase overheads as the completion mechanism may need to work with finer-grained notifications. Using a smaller number of receiver-side partitions may provide higher performance. In fact, we suspect that that's quite the case, but I can't guarantee that for all future solutions. Some solutions in the future might have some hardware that can help this, that you may be able to use a large number. So a large number of sender-side partitions may be aggregated by an MPI implementation, making performance concerns of a larger number of partitions less potentially impactful than receiver-side granularity. Basically, we can help you, if you do stupid stuff, we can help you more on the send side than we can on the receiver side. Advice to implementers. It is expected that a high-quality MPI implementation will provide best effort to aggregate data transfers for the requested partition counts on the sender side and receiver side to allow optimization for different hardware. A high-quality implementation may also resize data transfers for the partitions to combine the partitions into fractional partition size, e.g. 2.5 partitions for a single data transfer. I should mention here that before we have added the words high-quality MPI implementation, before we just said it's expected that MPI implementations will provide best effort, we added high-quality in this section. That's one of the major changes in this section. Aside from what's happened here is we've taken out all the references to MPI weight, and we added in that we're higher quality MPI implementation. That's the major changes in this section here. So first,
hey, a minor comment. Yeah, these high quality comments always kind of get me. I mean, would it be better to say that MPI implementations might be able to provide better performance by aggregating data transfers or something like that? I mean, this high quality thing it tends to be very sort of situational, and I mean, we have other instances where, you know, you could imagine the situation where that may not be high quality for a particular system. Right? I mean, wouldn't it be better if we said things like MPI implementations might be able to provide better performance by aggregating data transfers or something like that, rather than using this high quality?
We could.
Sorry,
I mean, originally
I'm just picking on. I'm just picking on
the
words. I'm just picking on the words. I think the advice is fine.
Yeah, so originally this read that it's expected that MPI implementations provide best effort to aggregate data transfers. Um,
But I mean, the usage model is also tied up in this too, right? I mean, if I have data that can be sent now, maybe I should send it now rather than waiting to send it later. You know, if the network's not busy.
uh, Agreed. So we could put this in terms of, I mean, the point here was you're supposed to provide best effort to aggregate where it makes sense. But it's not meant to say you should aggregate to the detriment of performance or system optimization, right? It's just saying you should try to aggregate this stuff if it makes sense to aggregate it for optimization.
Yeah, I mean, I'm picking on the words really. I mean, I agree with everything you said. I think that when we write high quality in the standard like this, it tells, users that all implementations should do a certain thing or they suck, and it guides implementers toward doing a particular thing, which might actually be detrimental in certain situations. I just don't like it when we say high quality. I'm sorry, I'll be quiet now.
Okay,
So for Jim,
no problem. This was added based on a request, so it wasn't originally here. Matthew's taking notes for me. Matthew, can you just highlight that line with some sort of comment on the ticket, and we'll see if we can write it in a better way.
sounds good.
Okay, thanks.
So this is Martin. I hope you can hear me. I agree with Jim. I think here the high quality implementation is not the right thing. Or you could say that the high quality implementation will find the right trade-off between aggregation and latency sensitive communication. Because there is enough scenarios where it would not be the right thing to aggregate.
Agreed. We'll make it so that it reads sort of like an MPI implementation should do what makes sense.
Thanks.
Okay. Great. So first thing that we sort of lead with, and this is different from some of the MPI chapters because we sort of provide a code example here to give you an idea of how this works, keeping in mind that this chapter is after all of the point-to-point and persistent stuff that's happened. So I know that nobody reads the spec, cover to cover in linear logical order, but what we're trying to do here is basically give existing users an example of sort of, this is how this looks a little bit different than your existing stuff that we've already introduced you to from point to point. This is sort of meant to be friendly to our users that have been around since way before I was involved in MPI 1, MPI 2 days when that are just familiar with MPI and just want basically a quick delta on this. So we open up with sort of like a very simple example showing how you would want to do these things. And this one is an example of a simple partition transfer in which the sender and receiver side partitioning is identical and there's no like additional threads introduced or anything like that. We have some examples with OpenMP type threading at the end of the chapter, but this is sort of a lead in for this is what we do. So I'm not going to read code on a telecom line because that's kind of crazy, but I'll just sort of walk you through what's going on. So we cleaned up this code quite a bit. So we have a set of doubles. Originally, this code from people who saw it last time, this code gave you an example of creating a contiguous data type of itself, or by itself that was a custom data type that you could use in this code. We've gotten rid of all of that. So now it's just doubles. We have a given number of partitions. You do an MPI init. You find your rank. Process 0 does a psend init, which is basically giving you the idea of a message. You get count of partitions. And then here, I need to make a clarifying statement here so people understand exactly how this works before you get into the meat of explaining how this works. You define a number of partitions, and then you define a count and a data type for each of the individual partitions. This is not the total number of data. This is not the total count of data or the data type of the entire buffer. It's just the individual partitions. So this expresses the partitions themselves. This gets us around a problem that if we declared this and said that the init was for everything, you get into these weird situations where you can't divide equally, and then it gets weird on how you define your partitions. So this sort of forces people into having fairly identical partitions. They can avoid this by using custom data types if they want, but we're not introducing this right now. Destination tag, MPI com world request, basically. You use a regular old MPI start, and for a total number of partitions, you end up calling pready for all of them. In this case, we called them in order. That's not a requirement at all in any way, but it just shows you how you use it. And then basically we test for completion while it's not complete. For the receiver side, we just need to do an init, similar thing that matches. We do a start while this flags, test for completion, free the request, finalize MPI, we're done. It's a fairly simple example and doesn't introduce any threads or anything else like that. Does anybody have any questions, comments about the example? Okay, great.
Ryan, I missed what you said about the derived data types in the init functions. Are derived data types allowed in there?
Yes, they are.
Okay, and so each partition would have the same data type?
Right now, yeah, we've introduced init such that each partition has the same data type for this init. What I was talking about with regards to how you could do things differently is the way that this init is set up, it allows us to do init v's and init w's later on and keep the exact same semantics that exist in the init. Sorry, that was me being unclear. Does that make sense? That we're defining this as an init with no vector or w nonsense whatsoever. But this definition will fit if we ever want to introduce init v versions and init w versions, which have varying data types, sizes, everything within multiple different partitions. So that gets really messy really quick if you start declaring those things.
Yeah, I'm just thinking about if I wanted to do a psend or a preceive on a column of a matrix, how that would work. Maybe that's something for me to work out offline. I mean, it seems to me like you would need to have some extra padding at the end of the data type or something like that so that you could stack them.
Yeah, you can do that with an existing, if you created your own data type, as long as the stride is consistent, you can do that with this existing one, right?
Right, but I think you need to add padding to the end of the data type so that when the next one starts, it's offset correctly from the previous one.
Completely agree. Yeah.
Yeah. So I don't know if we think that's a case, that seems a little bit subtle. It might be something that would be useful to have an example for.
Sure. Yeah, we had some data type examples, and we've got more examples at the end. We don't touch that particular example, but I'll make a note that we could potentially make one of these examples that way. Agreed. This first example, though, is purposefully extra simple, but we get into some more complicated stuff later. We'll make a note of that.
We need a simple example too. Yeah, absolutely.
So we've got some more examples at the end of the chapter too. So I'll show you those as well. But like I said, we don't have your exact situational example. It's a good example. We should consider putting one in. So thanks. Okay, advice to users. We say in practical uses of communication infrastructure, a higher level of send-side partitioning as compared to receiver-side partitioning is likely to be more efficient based on an MPI implementation's overhead in managing receiver-side partitions. This is the example of why you don't necessarily want to have a large number of receive-side partitions. Rationale. Partition communication is designed to provide opportunities for MPI to optimize data transfer. MPI is free to choose how many transfers to do within a partition communication send, independent of how many partitions are reported as ready to MPI through MPI ready calls. Aggregation is permitted but not required. Ordering is permitted but not required. This is ordering of partitions, right? A naive implementation can simply wait for the entire message buffer to be marked ready before any underlying transfers occur on the network. However, this modality of communication gives MPI far more flexibility than non-partitioned communications. Basically, you can end up turning this just straight into a regular old, ISEN type persistent communication, but you don't want to do that in your implementation. It's giving you opportunities for optimization. Hopefully, people will take advantage of those in their implementation.
Just a comment. Transfer occur on the network, but you cannot transfer not on the network. You cannot shared memory transfer, no?
Sorry, what was that? I had a hard time hearing you.
Oh, okay. So any underlying transfers occur on the network, but could you not do some partition communication in shared memory mode?
Yes, that's true. You can do shared partitioning in.
I don't know if I don't know if my remark is stupid or not actually. So I'm just trying to process what I'm saying. So I'm just the word I'm picking on the word the network, which means that it would be only possible for inter-node communication, and I'm just asking if that's the case or not.
Yeah, that was not necessarily implied. You could use partition communication through shared memory as well. So we'll make a note of that. We might just strike on the network and just say be marked ready before any underlying transfers occur.
Yeah.
Okay. All right. Thanks,
Matthew. Could I ask another?
Yep, you can ask another question.
Can I ask another just to help my understanding? Do you expect the implementation to use tags to part of the tag space to distinguish the partitions in a communication?
No, not at all. So the partition communication itself uses a tag to match, but the individual partitions underneath, we don't expect to go through a traditional source tag message matching mechanism at all. Doing so slows stuff down. So what I actually expect, if you ask me how I would implement this, I'll say this is obviously not the only way to implement it. But if I was going to implement this, what I would do is during the inits, I would wire up, for example, in today's networks, an RDMA buffer, and I would negotiate where that thing is, and then I would just send over a whole bunch of puts as different partitions, and on the last stuff, I would negotiate the closing of that buffer from an RDMA perspective, not an MPI RMA perspective. So ideally, if I had message ordering on my network, my last message that I send hopefully will be small, and I'll send a with notify kind of type thing with it. That's how I would implement these, so that you can check the individual partitions. In addition to the RDMA, you'd probably end up having, realistically in an implementation, another sort of side buffer that was tracking what's been written and where while it's happening, so that you can actually do the p-test type thing if you wanted to support p-test.
I guess the reason why I asked the question is I was trying to understand, there's a couple of instances in the text where there's a difference noted in performance implication of number of receiver partitions versus number of sender partitions.
Yeah.
Right, and I was trying to understand, I think it said that a large number of receive side partitions has a negative performance impact.
It can. It depends on how you keep track of it, right? So the idea here is that regardless of what you're doing, you still need to keep track of potentially a large number of receive side partitions. If you're doing something like, I don't know, an array of bits that indicates which partitions are written and which aren't, it's still a whole bunch of things you have to go through. If you're doing a more traditional matching solution, it's a lot of sub-requests that you have to go through. The idea here is just sort of to reduce the total amount of state that you're keeping on the receive side. And in addition to that, if you keep a lot of partitions on the receive side, the chances of why you're doing that is because you want to check a lot of them. And so you end up checking through that state a lot on that side as well, which will also increase overheads.
So there's, that part I guess would be application level. overheads if you're having to check a lot of individual things. I guess what I was thinking is that as I'm wondering how much this is tied to a particular implementation, because you could imagine an implementation which says, well, I can do 16 partitions efficiently, and that's the most that I'll support. And even if the user says, I want to do 128 receive side partitions, the implementation can essentially aggregate those and just say, I'm not going to do 128, I only support 16. So I'll tell you that the first chunk is done as a unit because, I'll basically take your 128 and break them up into 16 groups. Right?
Yeah.
I mean, is that reasonable? So I'm wondering if we're indicating to users that they should not, oftentimes what I'm thinking about is oftentimes we want the users to give the MPI library as much information as they can, so that MPI can sort of do the best thing possible for them, and so that you get performance portability, across different MPI implementations that might implement this interface differently. And so, I'm thinking, some implementations might actually be able to do 128 efficiently and give you benefit, and some other implementations would prefer a smaller number. And so I'm not sure, I'm just thinking through this advice that we're giving to users, and I'm not sure if it's good advice.
Well, even if you aggregate those things though, and then I call test any, for instance, right? It'll give me back that first section of the 128,
Mm-hmm.
right? Even though I've aggregated it in 16, what's going to happen is every time I call test any, I'm going to get back a whole bunch of different smaller receive side partitions.
Yeah, so on MPI implementation A, that might be the behavior. And then on MPI implementation B, it might actually be able to support those at the finer granularity, right? So if I'm an application developer and I'm going to write my, my chemistry code and run it on a bunch of different machines, what's the right thing for me to do in my application?
Yeah, the question really becomes, can you get the efficiency out of having all of those little tiny small partitions from your code in the first place?
Well, maybe. I mean, I don't know how small they are, right? It could be a large transfer, and breaking it into 120, maybe it's a 128 megabyte transfer, right? And breaking it up into 1 megabyte chunks might be reasonable for me to do from an application, or it might be connected to how many kernels I launch when I run this thing or something like that, right?
Yeah.
I'm just saying it feels a bit more subjective. I'm not sure. Like I'm trying to sort of mentally work through the advice to users. Like, hey, there's high overheads on the receive side. The overheads are maybe different on the send side, and it feels really connected to the implementation. And I'm wondering if, or it feels connected to a specific implementation. I'm wondering if the implementation already has ways that it can mitigate these overheads, whether this is the right advice to be giving users, or should they give the implementation as much information as they have about these partitions from their application and let the implementation try to figure out how to manage it?
It does, so encouraging, let's put it this way, encouraging a large number of receiver side partitions does force the implementations though into having to manage what to do when you get flooded with a billion receiver side partitions. It's a lot trickier to handle than the send side. The send side sort of falls out from how you'd probably implement this in the first place, that I expect that everybody will do it just fine. But on other networks, it could end up meaning that you're tracking and keeping state on a whole bunch of small messages.
Well, I might just set a size, right, and say, well, I'm not going to, if it's smaller than this size, I'm not going to track it, and I'll start aggregating in my implementation.
Yeah.
I'm sorry, I don't want to disrupt the whole thing you got going here. Maybe we should just take this as a separate side discussion.
It's good feedback. Obviously, the advice is non-normative in the first place, but I part of the goal of the advice was also to don't bog yourself down with a billion small receive partitions and requesting a ton of stuff from MPI, because actually asking whether a receive partition is complete or not could end up being a more expensive operation than you think. I agree with you though. I could think of new hardware in the future that made this trivial and you don't have to care about this anymore. This advice is somewhat contemporary for how you end up using contemporary hardware. Okay, let me think about that a little bit more. I'll highlight it for a little bit further discussion. Like I said, it's non-normative text, so giving it versus removing it is we might just strike it. So, thanks. That's valuable feedback, Jim.
Mm-hmm.
Okay, so let's get into the next controversial thing. This changed quite a bit. So for people who weren't familiar with the discussion that happened in Chicago, let me recap it a little bit so I can explain this, because this is probably the biggest thing that I want to discuss today and go over with everybody. When we had our init functions and we presented them in Chicago, there was a point made about whether or not they were blocking, how they connected, how they matched. We discussed how they matched quite a bit, and that's sort of resolved. But whether or not they blocked and whether or not they were local versus non-local and exactly what that means, I'm going to take some liberties with the discussion of blocking and non-blocking and local and non-local as they exist in the specification today, as opposed to how they are proposed to exist in the semantic terms chapters, because there's some very small modifications in those that mean big things. We will adapt this based on how that other ticket goes. But I'm just going to use the old language so that it's most familiar to everybody rather than getting into the semantic terms changes that are happening. So the discussion out of this was, wait a second, do these things have to match? Are they completely blocking? Can I get into situations where I end up with deadlocks because I haven't done things in the right order? How do I get around those things? And so we've come up with a solution for this, and let me get into it. So communication initialization for partitioning uses persistent communication APIs to initiate the message transfer. So this is just like persistent from this perspective. For such communications, invoking the operation, respectively doing the start, does not initiate transfer of any part of the user buffer, but may negotiate any, I want to highlight these things, it does not initiate transfer of any part of the user buffer, but may, does not have to, negotiate any required protocols and may optionally do other handshaking. It's not required to. Upon communication initialization, individual partitions of a message may be indicated as ready to be transferred by MPI via MPI ready calls. Ready calls.
All right, Ryan, I got another question.
Okay.
This negotiate the handshaking, the P send init does it block for the P receive init?
No, it does not. I'm going to get through sort of how this would function was what I was going to cover right now, which is not necessarily in the text, but I want to cover sort of the flow. Does it make sense? Can I do that first?
It may be something where we want to say it may initiate the handshaking or something like that, right? If the handshaking, it doesn't seem like the handshaking can complete until the matching call gets made, right?
Agreed, but it's not required that this is done by the time that init returns. So
Okay,
basically what the forum said, for a little bit of background, was, hey, this thing really needs to be, you need to have some sort of non-blocking init. And let me walk you through the thought process behind this. The existing init, we want it to be non-blocking and return right away, even if it hasn't matched with the other side. And basically, you would initially think that this is a non-blocking init, and so you'd end up with two requests. One for is the init done, and then one for what is the request structure for the entire thing that's going to be done after the init. This was tried in partitioned collectives, and the forum absolutely hated having 2 requests. So here's the thought process behind why we can do this in the init for the request. I'm going to cut down to some text down here that covers this. So I'm just going to, I'll read this text really, really quickly, but I want to get to the rationale to explain this topic. So this creates a partition communication request and binds it to all arguments of the partition send operation. This call is required to be matched with the MPI receive init call. Matching occurs as would a point-to-point communication using MPI send or receive calls, so it can happen afterwards. Partition communication initialization calls are non-blocking, and completion of initialization is only guaranteed when completion of the entire partition communication is returned and the request provided. In other words, you can hold off on doing your handshake. You can hold off on negotiating the buffer through an init and a start and all the p-ready calls that you want. It really only actually has to happen before the entire operation completes for the first time. Remember, this is persistent, so you can start it over again, right? There's no required text in MPI that says that any of this stuff has to have happened by this point. So you can, if you wanted to, init something, start it, call p-ready a whole bunch of times, and all that's really doing is keeping the application buffer, because once you've called p-ready, you're not allowed to touch that buffer again in that section until the test has returned successfully. So you can do a sort of a really lazy version of this, which means that having a request that tells you whether it's initialized or not is not actually, at least we can't find any good use cases for it. So that's where this rationale comes from, which is rationale. Did somebody want to talk?
Yes. Just a remark. So I know you mentioned that you don't want to synchronize this with not yet with the terms and semantics ticket, but here you speak about initialization, and in the text above you speak about initiation, which is 2 different things. So you need maybe to have something more coherent in the text. You say communication initiation, and then the initiation becomes initialization, which are 2 different concepts in the semantic terms ticket. So maybe you should have something more coherent here.
Okay, we'll double check that.
Okay.
Luckily, all the guys who do the semantics terms ticket, most of them are in the working group that's working on this. So we'll make sure that we've got that fully.
Yeah, because initiation is the merge of 2 steps in the semantic working group. It's initialization plus the start. So you use initiation here, and after you use initialization, which is not the same.
Yes, correct.
So you whatever the term you want to use, you should use just one, not 2.
Agreed. We'll fix that up.
Okay.
Thank you for pointing that out. Okay. So keeping that in mind, we put in a rationale here for why the init doesn't have an associated request with just the initialization phase. So the rationale is there is no separate request for informing the user as to when the initialization of a partition communication is complete. Implementations only need to agree on a communication buffer with the receive side process before any data is transmitted. This does not prevent locally starting the communication and calling MPI ready, as no data is required to move to the receive side from these calls. End of rationale. So the idea here is that basically this can be non-blocking. You can let MPI do it all behind the scenes, and you don't, because we don't even have we haven't defined that MPI wait is allowed for partitioned communication, because of the weird way that you can potentially stitch together partitioned communications that can be dependent on each other with p-tests. P-wait wait is just not a thing. So we say you always really need to use test with these to avoid you ever getting in a situation with deadlock. So the idea is that you can wait till the end of time with test as long as you have a receive and it eventually happens, you should be able to transfer this data at that point. But basically basically we can block initializing all the way into when you're calling the final test. So what does it mean to the user whether or not it's initialized or not? What extra data that they have if we tell them that this initialization is complete, do they get, and what can they do versus just waiting and saying, hey, your call completed? At that point, you know that the initialization has happened. And realistically, you're probably going to be going back and doing start test again to complete subsequent rounds of it as well. So we think we can make this entirely avoid the deadlock issue with a send versus a receive match on a state on the receiver side where you could potentially get into trouble. There's no reason why an MPI implementation basically can't avoid all of this. So an analogy I'd use again is, bear with me. One of the ways I can implement this is using RDMA on modern networks. So, calling for an RDMA buffer on a remote node is not a blocking thing. I can have multiple of those requests out at the same time and satisfy them. And since the ordering requirement is basically that these have to be satisfied from a given source only, doesn't guarantee multi-source interleaving in any given order whatsoever, we should be fine with doing this because the requests from an individual source can be actually ordered from the sender side to make sure that they always happen in a specific order to the receiver. And because the receive side is essentially the same thing with its receive in it, it can wait until whenever to actually handshake with the send side in it. We essentially get around the blocking / deadlock problem with these calls. So I know that's very different from some of the other solutions that have been proposed in the past for this type of solution. I welcome any stones people would like to throw at this, but we as a group haven't been able to figure out anything that that is a solid use case for why you'd care about this and why you can't do it lazily and therefore not have to block and not worry about the ordering requirements of the calls and blocking and matching.
So just a question. So when you call the psend init, just when you return from the function, then you can right away do a psend. Is that right?
You can. Well, you're supposed to call start first. So you do a psend init, then you can right away call start, and then you can right away.
Okay. Start. Okay. Start in between. Okay.
Yep. So that's where we say it does not prevent locally starting the communication, which would be the MPI start, and then call MPI P ready, because basically all it's doing is saying, hey, this buffer's ready. And if the receiver's not ready, the sender can't do much about that, right? So it'll just sit there and say, okay, great, I got my entire buffer ready. Well, I'm still trying to handshake with this other guy because he's just not ready for me. And then as soon as the handshake comes, then you blast out all the data.
Okay.
Right. Instead of saying locally starting, can we change that to say this does not prevent the sending process from starting the communication and calling MPIP ready? Like local has particular meanings associated to it in MPI, right? I mean, I think the last sentence, right, should say this does not prevent the sending process from starting the communication. I'm getting stuck on the word locally here.
Yeah, I don't think we need the extra requirement of the local, actually. So.
Well, I think the point is that this is a local operation.
Yeah.
In the MPI for the MPI definition of local.
Yep.
I mean, you might even want to throw the term in there somewhere.
The term meaning you mean local operation?
Exactly. Yeah.
Yeah.
But the locally starting, I don't think is specific enough. I think it'd be better to say the sending process there. Because I read that the first time and I was thinking about the receiver process because that's what the previous sentence talks about.
Okay. Yeah, well, we'll change that. I think it's more descriptive that way anyway.
I have a nitpick on the previous sentences as well. I think it's important that we try to make these things also make sense for an implementation that just doesn't do partitioning, that just essentially treats this as, delays everything and then sends it once the whole message is ready and expects the receiver to do the same thing, right? So essentially collapses it down to persistent send receive.
Yep.
So from that point of view, communication buffer is not really the right thing, right? It should be implementations need to agree on the communication parameters. Right? There's no, there's potentially more to it, right? There's a tag involved and things like that.
Yeah, so you're saying change buffer into parameters and A into the, to agree on the communication parameters? Okay.
And another nitpick. Do we use
Go
the
ahead.
terminology receive side process elsewhere, or do we say something like receiving process or receiver process, or just receiver?
So let me double check back.
We had this proposal to like replace process with MPI process. I'm just trying to remember what all we did there.
So we'd, in this chapter, been consistent with, this was pointed out before too, and we have receiver side. We'll double check, but we tried to go through and make it consistent through the entire chapter.
No, I think it's different, right? Because you're talking about the receiver, the partitions at the receiver, and this is talking about this is process. So I don't think we have receiver side process elsewhere in the spec.
Oh, okay. What do you know what the language is off the top of your head?
Nope.
We'll go back and double check it.
It may just be receiver.
Okay. We may want to say with the receiving MPI process.
That'd be fine.
So make less work for the MPI process ticket that needs to be going on for forever.
Yeah. Okay. Thanks.
Okay. Great. Thanks. Any other comments? This is a lot of the new stuff, so this is very helpful. Okay. I should mention that if anybody does after this call think of a solid use case as to why you would ever care whether the communication was actually initialized before you actually found out that it was completing in some way, right? You can also call p-test functions for individual partitions. And, if you get back a p-test result, it was initialized as well. We don't really have a use case for when we think we care whether it's initialized, truly initialized or not, before you start receiving anything, either an individual partition or the whole operation done. If anybody can think of some use cases for it, please let us know. But otherwise, we don't have any compelling reason to add a second request to these. And I think the second request is kind of ugly anyways. So okay. Continuing on.
Hey, so your count's an integer. Is that right?
Yes, the count is a non-negative integer.
Okay. We sure about that? Sorry to pick on it.
So this matches what's done in sends today. Now we
I
have
know.
we have so there's a compelling reason to change this into an MPI count type. It's possible, we haven't worked through all the details about this, but if we changed all this stuff into MPI count types, it's possible that we could avoid the big little problem with 64-bit MPI, and you could use partition communication for it. We're considering such a solution, but for now it matches what's done in send and receive.
Yeah, even for partitions, right? I mean, I think it'd be better to use MPI count for any new interfaces that we're putting in.
Yeah, we're definitely considering it and going through all the ramifications of
So how important is it to be parallel to send and receive and I send everything? Are you allowed to match them? Can I do a partition communication, send and receive with a regular receive?
As we've defined it right now, the answer is no. There's no technical reason why you couldn't necessarily do a MPI receive, persistent receive with a partition communication. You could, in an MPI implementation, wire these things together underneath the covers, and you could do it. You'd just get a notification of the entire buffer on the receive side, for instance. I don't think we necessarily want to do that, which is another reason why we're leaning towards doing MPI count for these things in the future too. So MPI count could provide us with a send receive type thing, because you can always use partitions with a number of partitions equals 1 and essentially get regular send receive semantics. So using MPI count may be a good idea, and we're just working out whether or not there are any hidden pitfalls here. But we may end up proposing this when we pitch it in Zurich.
So I'm not necessarily disagreeing, but why do you say it's not a good idea to match? What's the drawback of having them allowed to match? Just more ifs in the past?
It's just whether or not MPI implementations would support it, because you have to set up something for partitions to be received into, right? It's not like a traditional something comes in and you have a tag and source and communicator, and once you match that thing the first time, there's no concept that you would then hold that same entry to have multiple things come into it, right? So it's just that there's a ramification to MPI implementations. The way that you do a basic receive today wouldn't necessarily just straight match up with what we're doing. There's still a handshake that needs to happen underneath the covers. You could do it. There's no reason why you technically couldn't do it. Just if you tried to do it today with no modifications, it wouldn't work.
So I can see that if you have the same partitions on sender and receiver, but if you have an arbitrary number of partitions on both sides, you don't have a chance. You basically have to do a bunch of arithmetic on the receiver side anyway to find out which partial buffers are there. So I don't see there's much difference at this point. Or is it just more complicated than I think it is?
So let me see if I understand what you're saying. Are you saying that you just want to match a MPI P send init and just post on the other side an MPI receive?
Yes. Yeah.
Yeah. So.
But this is what I'm saying. You said that it has to be a complete different type of receive setup and things like this because you want to receive straight into the partitions. But that actually only works if the partitions are the same on both sides. So that special case where I can do it differently is not the case. It only works in some cases, right? If you have like 3 partitions on one side and 7 on the other side, you have to do a whole bunch of filling in, measuring what partitions are full anyway on the receive side. So you probably have to have a receive buffer there. You have to handle it with the message. So I'm not sure how much different you can actually handle it than if you would just have a straight receive there. Is there really a handshake between the sides if the partitions are matched?
Sure, you can work all.
So I'm playing a little bit devil's advocate here.
Yeah, I'm just saying that all you have to do is an existing implementation. If you call the receive right now, right, there's no concept in an MPI implementation right now that you could potentially be wiring to a partition send. And the send is going to send multiple data messages over to you that are not really truly MPI messages. And so the way that you've potentially done an implementation today, like I said, there's no technical reason why you couldn't have an MPI receive match up with an MPI psend init. I'm just saying that not all implementations would actually support that straight out of the gate. We'd have to like define it so that everybody changed it all at once, that this was actually, no, you can actually do this thing. We have not defined that way just because we're not requiring MPI implementations to have to wire up to go back and modify their MPI receives. Because the other thing is that if you do an MPI receive that way, you do have to do a check when you post it to say, hey, if this could match with a persistent, like a partitioned init, send init, in which case I have to do something else with it in the future. And so you'd have to check it in a different way. It could add some extra ifs into the receive pipeline, and potentially, and we're very reticent to do that. So that's the only reason why it's not in there right now, is just because we don't really know exactly what the ramifications would be for all the implementations. But I know that, for example, like in OpenMPI, I'd probably have to add an if to the receive to try to figure out if I'm going to receive a whole bunch of underlying primitive data network packets into this single thing, or whether I'm going to expect that it comes in the typical fashion. It's not a huge change, but I'm not entirely 100% certain that I can tell you that you could function with the receive as it exists today with no modifications. Really depends on how you do the implementation.
Okay, now I see where you're coming from. So I was just playing devil's advocate to make sure we play this through. But basically, it's also an implementation argument, right? Otherwise you would require people to change the receive path that exists, and without it, they can just add the new function basically independently.
Exactly.
Yeah. Okay.
I didn't feel like there was enough of a win there to require everybody to change their existing receive paths. So, but we are, because of that though, because we've made that decision now, because we were going back and forth with this at the beginning too, we may be able to move these into MPI counts now, which could provide us with a nice little way to be able to provide 64-bit counts here.
Right, and in this case, that's kind of why I started the discussion. If we are sure that's the right thing to do, and we seem to be going that direction, then I would fully support the 64-bit right away, because otherwise we'll have to deal with it later on.
Yep, and it does give us a nice addition for MPI4, which is, hey, there's this new point-to-point type stuff you can use, and if you just use one partition with it, hey, it's like big count. So if you need 64-bit counts, just go use this partition thing with one partition for now, and it's essentially the same as doing some iSends and iReceives with big counts.
Yeah, that
I'm
of
not
course.
saying it's the end solution.
Yeah.
I'm just saying it's at least something we can point to and go, see, we do have some point-to-point communication that you can use a 64-bit count with. It just may not be the exact type you want to use.
Which then people would scream immediately for an IP receive and an IP send.
Which I have down as, make sure you make a separate ticket for IP send and IP receive.
Okay, fair enough.
We intend on doing that. There will be a separate ticket for what I call if send and if receive. But I'm not going to put it in this particular ticket, only because I think it's useful. We'll tack it onto another ticket. People want it, they can vote it in addition to this stuff. So that's just a timing thing. So we'll bring along another ticket for Zurich, hopefully that has those versions in it. Because Pavan wanted that as well, right? So, okay. Any other comments, or keep going? We're almost at halfway, and we're almost halfway done time-wise. So, okay. So receive is basically the same thing. Creates a receive request. It's required to be matched. It's essentially similar language for almost all this stuff, just on the receive side. It's only guaranteed when the completion of the entire partition communication is returned in the request provided. So again, the initialization call is essentially non-blocking. Okay. Next call, p-ready, which takes a partition number and it takes a request. So we fixed there was a small error, I believe, in the Fortran. We fixed that up. It says MPI P-ready indicates that a given partition is ready to be transferred. Partitioning is defined when the persistent operation is defined. Specifying a partition number that is larger than the number of partitions declared in the MPI psend init call initializing the operation is erroneous. After a call to MPI start, all partitions associated with that operation are inactive. A call to MPI P-ready marks the indicated partition as active. MPI P-ready shall only be called for inactive partitions. That's it. That's basically the rules for P-ready. We are going to reference those rules now in the next calls. So there's another one called P-ready range. This allows you to give a low and high partition count and say everything between this range is done. This is useful because it can sort of define blocks that you already know that an entire block is coming in as contiguous, which could be useful to the MPI implementation. So with P-ready range, we have partitions marked with MPI P-ready range can be transferred in any order, in groups, or all at once. There's no ordering implied by MPI P-ready range. And then we define it a little bit more tightly here. A call to MPI P-ready range has the same effect as calls to MPI P-ready executed for I equals 0 to some count -1 in some arbitrary order. Calls to the MPI P-ready range follow the same rules as those for an MPI P-ready call. Those would be all of the you can't call P-ready on an active partition and that sort of thing. So this language is requested to be changed. We did change some stuff here. Namely, the second sentence has been added, which aligns it a lot better with the existing persistent communication and how these things are defined for things like start all. So this is very similar in those sort of languages. And we've referenced all the rules back for MPI P-ready about the initializing of going above the number of partitions. There was no reason to repeat that text here.
Should it really be called 0 to count -1, or should it be low range to high range?
Well, I considered that when doing this too. We could do high range. We could do, 0 from low to high.
Because 0 implies to me the beginning.
That might be more descriptive. Let me highlight it and we'll consider it. I might actually want to change that. Thanks for that suggestion, Martin.
Well, there's no count argument to the function.
No, yeah, it was meant to be that it wasn't meant to be necessarily the function count. It was some arbitrary count. I'll change it from high to low to make it specific to this call.
Yeah, the other comment I had is that I think that the fact that the partitions are transferred in any order is mentioned like 3 times in these 2 sentences, and that's probably 2 times more than we need.
We could strike the original first sentence.
Yeah, I think, the first sentence, you could just remove the whole first sentence, and I think it'd be fine.
Okay, let me highlight that. There was some discussion on whether or not to drop that sentence before some of the other text changed.
Yeah, I mean, that sentence itself, says twice that they're transferred in any order. So if you were to keep it, we should at least trim it down.
Yeah, we could say can be transferred in groups or all at once. There's no ordering implied. And it has the effect of calling these things in some arbitrary order.
If you were to keep it, I'd say it can be transferred in any order, and then, for example, in groups or all at once, and then delete the rest of the sentence.
Yeah.
There should be a for example before in groups or all at once, because it's not. There are other unordered transfers. Right, individually, for example, is not. You don't want to get into that being a fully inclusive statement. Okay,
let me go work with that sentence because I want to keep the fact that it can be transferred in groups and in entire blocks. But in terms of ordering, it can be, as if you just executed P-ready in some arbitrary order. It doesn't have to adhere to any order at all. So that's the intent there. I'll go back and work on this one sentence a little bit. So you'll have the exact same complaint about this next section. I'll make sure P-ready list does the same thing. The difference here is that the partition list is not high-low. It actually is some sort of count for the overall list size. It actually is count. So, all right. Any other comments on that?
Can that count be an MPI count also?
Potentially, yeah. If we go through and we change the counts associated with this stuff, we're going to change them all.
Mm-hmm.
Okay. 4.2.2, communication completion under partitioning. So the MPI test function. So this is the major change through this section for people to know is before we referenced a whole bunch of stuff with respect to weights. Weights have some issues where you can get into some interesting deadlock conditions when you're partially complete and you wait on other things that are partially complete. So the solution for those is just because we have these weird partially complete functions, the safest thing to do out of all this is to just tell people to use test. Don't use wait on partitions. So you'll see that we refer to test and the test any, test some kind of things relatives. So the MPI test function and relatives are used to complete a partition communication operation. The completion of a partition send operation indicates that the sender is now free to call MPI start to restart the operation and subsequently MPI P ready for locations in the send buffer. Send buffer itself leaves the content of the send buffer unchanged. It does not indicate that the partitions of the message have all been received. Rather, it may have been buffered by the communication system. The completion of a partition receive operation through MPI test indicates that the receive buffer contains all of the partitions. Functions for probing the partial completion of the receive buffer are provided with the MPI p-test family of functions. The MPI p-test call can be used to determine if the message data for the indicated partition has been received into the receive buffer. The receiver is now free to access this partition as well as any others that have previously completed for that operation, and that the status object is set for this partition. It does not indicate that the matching send operations needed to fulfill this partition have completed, but indicates that such sends or sends were started. This is just the weird definition of completion with regards to you don't know that everything's done, but you can find out that your particular little bit of data is available. Note that the send and receive partitioning are not required to be the same, so there is no guarantee of one-to-one correspondence between receive partitions and send partitions. For example, partition number 5 being ready/sent on the sender side does not mean that partition number 5 on the receiver side is received. So it's just, you could have 20 send partitions and 100 receive partitions, or you could have 10 send partitions and 5 receive partitions. The numbering between them has no correlation whatsoever. The partition number on the send and receive can't necessarily be matched. That's all. Okay, that was a lot of text. Any comments, questions?
So the one thing I missed before, perhaps because just because I didn't see the screen fully. So you said we only have tests, but that's for the P test, right? I can still use an MPI wait on the overall request, or not?
Well, MPI wait can get used into some interesting scenarios. So wait is essentially just equivalent to calling test in a loop anyways, right?
Well, not quite, right? I mean, as one is busy waiting, the other one gives MPI the chance to do something useful.
True. So definitely don't have a Q wait operation. I guess there's nothing that absolutely stops you from using. You have to be really careful how you use it.
So did you say P wait or MPI wait?
MPI wait.
Okay.
Nothing stops you from using MPI wait. The Q wait is a bad idea. Don't do it.
Right. Okay. That part I think we covered in Chicago extensively, right?
Yeah.
But not allowing MPI weight would make the whole request concept completely non-orthogonal to the rest of the standard, which I think would be a bit of a problem.
Yeah, agreed. Let me go back and look at this. I think we actually, this is like last minute. I might have messed this up at the last minute with search replace. Let me go back and look at it again.
Okay.
Okay.
Ryan, I've got another question on that first paragraph. Is it necessary to say that the send operation leaves the content of the send buffer unchanged? It should be a const argument to the send operation.
Yeah, that might be superfluous language. I mean, it's true, but we might not need to say it. Let me highlight it for, I might just cut it.
Didn't we add this at some point to all the send calls as part of the whole const discussion at some point? So I think initially MPI was allowed to immediately rewrite the buffer, but when it returns, so when the operation is complete, it would have to put everything back. And I think we wanted to prevent that, so you're actually allowed to read from a send buffer even while the send is in operation. I don't know if this is language we're taking from other parts of the standard here. I would have to check that. I just thought I remembered something in that direction.
Yeah, interesting. Okay.
I've highlighted it. I'll double check it. I think that you're right, Martin. I think that might be where this has come from. That we wanted to make it consistent with other sections of the standard.
In that case, it's even stronger, right? It's not just that it leaves the content of the send buffer unchanged. It's that it does not modify the content of the send buffer. Right, because the P ready is, right, the send is, it's a non-blocking send operation, right? So the MPI is utilizing that buffer, during some window of time, and, even during that time, it's not modifying the send buffer. So it's, right, I'm picking on leaves here, right? Leaves says that after the operation, the contents of the send buffer is unchanged. But what Martin was saying is something even stronger than that, is even during the operation, it doesn't change the contents of the buffer.
I thought that's what we intended when we made the change for the send. That was a while ago. I think it was even before, during the 3.0 time frame when we had that discussion. So we actually have to look back to. But I think that was the intent, yes.
Okay. Well, I'll
make
sure that this is consistent with the other sections and the text. I'll go back and double check it. I agree. I think the intention was modification, not that it ends the operation with the same content. You can modify it in between. That's kind of wacky anyway.
Right, so I think the best thing I agree would be to do to go back, check if it's consistent. And if you see a problem with what is consistent, then we should have a separate ticket of fixing it afterwards.
Yep. Okay, let me take a look back at that, because I'm going to have to dig through other parts of the standard. Thanks for pointing that out. Okay. Any other comments? Okay, great. Let's get into the p-test functions. So p-test functions, same thing applies here. Integer may turn into MPI count. So we have a partition, a flag, a status, and a request. And basically, this is the same way that you do a general test, except that we're adding in basically this partition solution. So a call to MPI p-test returns flag equals true if the operation identified by request for the specified partition is complete. The request is partitioned and therefore is not marked as complete / inactive by this operation. So this is the same thing as, if you, we don't want to actually complete a persistent operation by this in any way. This is not leading to completion. It's just informing you that that particular partition happens to be there and valid. A subsequent MPI test operation is required to do the normal completion of the whole message as described in Chapter 3. That should say MPI test / MPI wait. One is allowed to call MPI ptest with a null or inactive request argument. One is also allowed to call the test for a partition that has already been completed without subsequently being restarted. In either case, the operation returns with flag equals true. The function MPI ptest can be used to test partial completion of both send and receive partitioned operations. Basically the same way, the following very similar rules to what happens if you want to poke at a persistent communication without making sure that we don't actually imply that we're completing anything or that you won't get further messages from these things. So ptest is sort of meant to be independent of your test wait. Your test wait is telling you about the whole operation. Ptest lets you sort of peek into it for not quite finished stuff, but that doesn't modify any of the state of the request whatsoever when you get these values out. It's basically just reading whether or not something is partially complete in there and whether or not you can read that particular portion of a buffer. This is useful for, if you're running a multi-threaded solution that's, for example, task stealing or sharing in some way, you can, or just doing regular many threads, each looking for an individual task. They can all probe for their individual data that's available and start working early on a given amount of data that's come in without having to wait for the entire buffer to be complete before you can start work.
Hey, nitpick on between line 5 and 6. Instead of to do the normal completion, could we write to check for completion?
To check for completion instead of do the normal completion. Yeah, I agreed. Okay, cool. Hopefully Matthew got that. If not, we'll cover it in a little bit. Matthew's taking notes for me, so. Okay. Thanks for the nitpick, Jim. Okay, next. Semantics of non-blocking communications in partition mode. The semantics of non-blocking partition communication is defined by suitably extending the definitions in section 3.5. That's back to the non-blocking communication section in the partition point-to-point chapter. Interpretation of count and data for partition communication. Partition communication uses the count and data type arguments in the partition communication initialization functions to describe a single partition. The argument partitions specifies how many partitions of a number, count, of data types make up the entire buffer to be transferred in the partition communication. Once a partition transfer is started, each partition must be marked as ready using MPI ready, and the operation must be completed using the function completion function MPI test / MPI wait. So all that's basically saying is the count and data type describe an individual partition, and then you say how many partitions you have.
Ryan, I think it would be good to give a little bit more explanation about how the partitions and the data types relate to each other, which is, I guess what I'm thinking about is this case I mentioned earlier about the, it's considered to be a sequence of the data type times the count. And so if you're only thinking about basic data types, this is sort of obvious and pointless to say, but if you're thinking about derived data types, like if you're trying to take a column out of a matrix, the fact that, I don't know, maybe it's just too obvious to say, but do you see what I'm getting at?
Do you want, I'm not exactly sure what you want. You want more of a discussion of the relationship between the data types and how they make up how the data type count and data types work between multiple different partitions?
I think what I'm looking for is just like a more formal description of what's already written here. which is to say that it's a sequence of count count data type segments or something like that.
Okay. You just like some more exact language for exactly how these things are put together.
I mean, the word we're talking about that we use count data type arguments and this number of partitions, but I think there's an assumption in this text that this describes a sequence of these partitions, and I think it would be good to actually make sure that we say that. Right. I mean, if a user wants to have these non-contiguous data types, they're actually going to have to get fairly technical about how they put these things together so that they line up and catch the right data.
Yes. Or, well, I have to be careful how I write this too, because we could add, V and W versions in the future that would make this potentially a little bit easier. So you could define them. Even for weird cases where you're not necessarily doing a column, you could express anything with those.
And there's other things too, like absolute displacement in a data type probably does not make sense for partition communication, since it's the same data type that's used for every partition.
Correct. Okay, let me make a note of that. I'll make sure we run through the different stuff.
So just because you said that, I have to really think through this too. But one use case we had for these absolute addressing with the bottom was a tools layer that we did for piggybacking. So we basically intercepted every call, created a new data type, added a piggyback with bottom to it, and then the absolute address of the data buffer we're sending. I guess this wouldn't work then here, right? So excluding this from being able to be piggybacked?
I think it would work if you had this this vector version where you have a different data type for each partition. In that case, I think you could do it, but yeah, not for this current API. I don't think you can.
Yeah, I guess you could just replace the communication to a single one count, single partition. That would work then again, but that would destroy the benefit, of course.
Mm-hmm.
Yeah, okay.
Okay. All right. Great. Well, I'll take a look at this more and make sure that we've got all the text in there to cover these corner cases. All right. Ordering. This basically says partition communication initialization procedures on the overall message are matched according to the matching rules specified in section 3.5. So we're just basically saying whatever happens inside of a partition communication, but we order them the same as if they were just regular messages on the overall transfers, which is no different than what you'd be doing for persistent communication today. So this really doesn't make a change to almost anything. Just to make sure that everybody knows that they don't need to modify any other portions of their implementations with this. Okay. Multiple partition completions. So it's convenient to be able to test for the completion of any of the operations in a list, multiple partitions on a single request. So note, we've cut this down quite a bit now. We only support test any now, because this is the one use case that everybody could see things for. The other types of test we don't have now. So a call to ptest any can be used to test for the completion of one out of several partitions of a single request. The other ones got messy because you could use multiple requests and this sort of stuff. Oops, and I just noticed a typo in here. This shouldn't be array of requests. So this basically will just give you back a I want to see if any of the partitions are complete and spit back a partition at me. And the procedure tests for completion of one or none of the partitioned operations associated with active handles. In the former case, if I equals true, returns an index. The index is this request in the array, the partition in the array, sorry. And in the partition of the partition operation completed in the index array. Did I mess this up? Hold on a second. If the request is an active participant request, it is not marked as an active. The request is ephemeral. It is not deallocated, nor is it set to an MPI request equals null. A subsequent MPI test operation is required to do the normal completion of the whole message as described in Chapter 3. There's some screwed up text in there. I will fix that. I didn't realize it before. Sorry about that. But basically, we just want to be able to test for any of the partitions in a given operation. So if you take a single partitioned operation, single request, I want to be able to just be able to say, give me back any of the partitions that are available for this. That's useful for, a multi-threaded context where all I'm trying to do is get data to work on. I'm not trying to care about a particular portion of the buffer. I'm just going to be a thread or execution context actor in some way that just wants a piece of data out of my receive side buffer. And I don't care which portion of the data it actually is. So this lets you fetch that. We put in here that the array is indexed from 0 and C and 1 from Fortran, all the regular stuff that you have with this. Active handles on the execution of test any has the same effect as calling ptest on the whole thing from one count in some arbitrary order until one of the calls returns flag equals true or all fail. In the former case, index is set to the last value of I and partition is set to the partition of the unauthorized complete. I have to get rid of the stuff that talks about the array of requests. Sorry about that, folks. But the partition will be set to the partition of the operation that completed. In the latter case, they're set to undefined because if you test any on this and in that request there are no partitions that are defined, you get undefined back. No partitions that are completed, then you get back undefined. So it's basically just a way to avoid calling ptest in a loop on every single one of the partitions. You can just call partition, ptest any and get back partition number. So, okay, next section. Any questions on that? We did get rid of some and all to let you do stuff on all of the different array of requests, which, sorry, should have been out of that one as well. But we didn't really have really good reasons for them, and they got really, really messy really, really quickly because you had both the requests and then the multiple parts underneath the request, and it leads to this huge n by n type situation that's bad.
Is ptest all equivalent to just doing MPI test on the persistent handle?
Yes. So there's no point in really having it.
It could be useful to have like a, note to users in there somewhere, right? That is, if this is what you want, then, you might as well just do test on the handle.
Well, let me take that back though. ptest all technically would, if you define it the same way as persistent communication, would be an entire set of all the requests. So you'd have multiple. You'd really be testing for partition completion in multiple different partitioned operations at the same time. So you'd get back like, hey, test all of my stuff. Tell me that this particular request has this stuff done and this particular request has this stuff done. It's really weird if you try to sort of follow the semantics of the existing tests or test any, all, some, those sort of things. We didn't really have a good case for why you'd want to test across multiple different partition communications, partitioned requests. So if we wanted to follow
maybe I missed something. Does ptest any, is that testing across different partitioned operation, or is it testing for any partition in a given operation?
No, it should test for any partition in a given single request. I'm sorry, the text was a little confusing there because it was not correct in a couple spots there that made it imply that it worked across multiple requests. That is not the intention.
Yeah, so I guess what I was saying is that if you wanted to test for all partitions in a given single operation, it ought to be the same as calling test on the operations handle. Just calling MPI test on the operations handle.
Agreed.
Okay, then sorry, I missed the other part where you were talking about multiple operations.
It's just that it doesn't quite match up. So the definition of these calls don't quite match up with what like the MPI test any, test some, test all would actually be. There's a weird sort of we are slightly decoupling what it means to do a p-test any is not the same as an MPI test any. It's not the exact same semantics. Because a lot of these work on arrays of requests, and we don't want to work on arrays of persistent communications, right? And
so essentially we already have a p-test all operation. It's not going to be more work for implementers to add it since they already have to implement it, right? As the MPI test on the request, we took it out mostly because we didn't like the standard use for it.
Yeah, you essentially already have the functionality for p-test all, right? Because you can just test the entire function. You can just test the entire request, sorry. So what exactly would be the purpose of p-test all when you can just do a p-test? I mean, I can put in a note, but...
I guess I'm just wondering, users might see this and they might see an any, and they're wondering why there isn't all or some. We could at least tell them that there is all, it just has a different name.
Yeah, I mean, I could put in a note to users. This doesn't exist because, this reason. You should just call this instead if you're looking for that functionality. Non-normative text is easy to add if we need to. I'll put a note for it and we'll discuss it with the group.
Yeah, I'm trying to decide if it's a bad idea, but I guess we can easily delete it if we don't like it.
Yeah.
Okay.
Okay. All right, so here are some examples. So we're almost done. Partition communication examples, and I don't know why there's a straight end there. Let me fix that. Partition communication with threads and tasks. Equal partitioning on send side and receive side examples shown in 3 is shown below using non-equal partitioning. In this case, the receive side uses a single partition while the sender uses 8 partitions. Note that these functions are like each other in the previous example. So basically what's happening here in this example is, remember the first example that I showed you was fairly simple. This one actually makes a contiguous type of MPI doubles, so a custom data type, commits it, initializes number of partitions with a count, but of expert type. So this is another way to sort of define something. So in this case, you might have, for example, count equals 1, but expert type was 5, 5 doubles in a contiguous data type defined. And so you can psend init it, you can start it, then we're going to use a parallel for going through and doing something that we're trying to indicate here in the comment, calling pready, and then testing for it after the fact. And then on the receiver side, the my rank equals 1, we have the init, we have a start, and then basically just wait around testing this thing, or do a wait. So this is just the basics that have been added here are OMP parallel loop, and the idea that you can use your own user-defined data types in these calls as well.
Hey, is the count that's given there in psend init, is that not 1?
Yes.
It is 1. Okay. Got it.
Yeah. So this is just showing you, hey, you could also compose these things together. It's essentially equivalent to calling like if the MPI double, in this case part length is 16, but it's essentially equivalent to saying partitions and 16 MPI doubles.
Mm-hmm.
I just wanted to quickly note that one of some of the text at the top actually refers to the next example rather than this, particularly the receive side using a single partition.
Oh, yes, the receive side does use a single partition in this case, right? Or are you saying that's the next one, Matthew?
In this example, there are multiple partitions on the receive side, so they're equal. In the next one, we do the one receive side partition.
Oh, okay.
Then the last example.
Which is the one I just scrolled to now. This one was saying it's tailored for send-side partitioning using threads. This is an example where a parallel task produces input part of an overall buffer, and they complete in any order and contribute to the overall buffer. So we've got similar setup at the beginning. We have partitions in part lengths, receive. This is where the receive partition is 1. So this is different partitioning. So thanks, Matthew. We'll change that one sentence. I have to copy paste it. And then we have an it. We create a contiguous data type again. We do send. The difference this time is there's task in here where you can actually, a little bit of formatting there. We'll fix that up. Where we actually do a p-ready on requests out of individual OMP tasks, and then we test for completion. This other side is the p-receive init. It's receive partitions and receive part length, and so it is only using one. It starts and then it tests on the whole thing. So it shows you that you can have different numbers of send side partitions than receive side partitions when this is the example that does it, not that first one, sorry. And that's the end of these examples.
Hey, Ryan, I missed the OpenMP code on the screen, but does that produce the exact number of partitions that the operation expects?
That parallel? It is not defined in this code what the OMP task number of tasks, num tasks or whatever is. That's an environmentally defined variable, right? So you could assume that would be very true, but it doesn't necessarily have to be.
So, I mean, this is a bit risky for users to do this, though, right? Because the code may very well deadlock if the variables aren't set right when you run it.
Correct. We should probably define them up at the top because we can modify them after the fact.
Yeah, or minimally have some kind of a check that it's the right number. I mean, or you could have reverse problem too, where it calls p-ready with invalid partition numbers.
Yes, too few times. We should put in a check there.
Yeah, too few or too many.
Yep. So we'll add an extra line to that. Thanks, Jim. That's a good point. The goal of this was to make it all easily copy pastable as examples so that they actually run.
I don't think we would want users to just paste that, though.
No, I don't. But I'd still like them to work if they did do that. So
they won't, though. I mean, right? If you set a different, you run this on one machine that's got so many cores, and you run on another node that's got so many cores, and the number of threads you get is going to be different.
Oh, agreed. So we'll have to tie the partition numbers, or we'll make sure that we define up there that only the thread numbers that are less than or equal to the partitions, and we'll check that the number of threads is at least equal to or greater than the partition numbers that we intend to send.
Yeah, I mean, if you want to do, if you want it to be reflective of what users might do, I think, you mentioned it in there that, like, you would partition the message according to the number of threads.
Yeah.
Right? And I think that's probably what users would want to do.
Yeah, partitions equals OMP num threads.
But then that highlights the corner case where the partitions all have to be the same size. So you may have to write some other code in there, right, to deal with the case where, let's say the number of threads doesn't evenly divide the message size.
Yeah. We'd have to take, for example, we might just want to do an example that takes the, highest power of 2 that is available for a number of threads and use that as a partition number, for instance, or something like that. Yeah, I agree. We'll go back and take a look at this just to make sure that we do all the checks for it so that we don't end up with bad code. Thanks for pointing that out.
Mm-hmm.
All right. With that, that's the end of this chapter. I will ask this too, since we've got a fair number of people on the line. What do people think about the debate between using integers for count or using MPI count? We're heavily leaning in the direction of using MPI count at this stage, but what I presented to you today was the safe bet because it's the same as what already exists. Do people want to use MPI count for this? Does anybody have any objections to using MPI count for this? We see some big benefits here to using it.
Assuming if you're sure that you never ever want to match it with existing MPI point-to-point calls, then I think doing it with count is the right thing.
Well, this is the debate that we've been having, right, Martin? Is it enough? Is what we're giving up reasonable enough that it's good for the benefits of using MPI count? And I think the benefit analysis out of the group so far has been leaning towards, seems like using MPI count is the better solution of the two. Even though we might give up some interleaving functionality, we just force everybody to use the psend and preceive init functions, then we're good to go. So this is sort of a debate that I think you could come down on both sides of it. I personally think that I don't speak for the group, but I personally think that the MPI count solution provides more benefits than it provides drawbacks.
So I don't think that using, sorry, we're getting a lot of noise on the line.
That's probably me, sorry.
Oh, thanks, Martin. I was going to say, I don't think that having an MPI count on the count argument here precludes using this together with an MPI send or an MPI receive, right? Because we already have different data type descriptions at the send and receive side, right? And I think it essentially boils down to the same thing, right? You have some description of the data layout at the sender, and you can use a different data type, or whatever, and the receiver, describes their data buffer layout independently using data types and count arguments.
Yeah, I think that's a fair point. It's really more that you break orthogonality at this point, right? Which people don't like to do. But you're right, we're technically not closing it. So that's a good argument for just doing it. If you really need to change it afterwards, we still can.
Yeah. Okay. Any other thoughts on that topic? Okay. Just one last sort of chance to solicit feedback from you guys since I got you for a few more minutes. Does anybody have a problem with the way that we've defined our init? Because we think we've worked around a major problem by defining them this way. It's saying, well, since you can be really lazy about when you actually initialize, you can just go ahead and call these things, they can return right away. It gets us around ordering blocking issue, but it technically is not the way that you would, if you followed the exact way that you do this in MPI today, you do something more like what was proposed for persistent collective communication, which was, you have two requests. Does anybody see a valid use case for knowing about when this thing is initted? Because with the collectives, there was a valid use case for trying to know when you'd actually completed the initialization, because it implied that you'd also negotiated some potential optimizations. In this case, that's not necessarily the case. It's not a, it's a point-to-point, it's not collective. So anybody have any major objections to that, or do people like what we've got as sort of solving the problem, or comments? I'll take positive feedback too, in addition to negative, if anybody wants to have it.
So Ryan, I'm trying to think of this from the application developer's point of view. Is there anything, knowing that it's initialized, does that change the application, what the application can do in any way? I mean, I can't see how it does.
Yeah, we can think of no reason why this information is important to the application, which is why we think it's okay to do this. Because knowing that it's initialized doesn't really impact you in any way. I mean, what does it do? You don't change your behavior. There wouldn't be any change in your behavior from an application perspective, knowing that your partition communication was initialized or not. I mean, aside from the fact that, you might not, you could, I guess, if you wanted to, check if it was initialized or not a whole bunch of times and just store up all your P-readies and do a single, here's all my stuff that's ready at once to try to avoid function call overhead. But, the use case for that seems so minuscule I don't think you could even observe the performance benefit of doing it necessarily, unless you were doing some crazy partitions, that knowing that it's initialized is useful.
So from a performance tuning point of view, if the user wanted to make sure that the negotiation was all done and set up, for example, I think Khaled had a paper on, how you might use this together with like kind of with an offload model, right? Where you, where you might want to set up triggered communication that that's going to fulfill these partition operations, right? And you want the accelerator to be able to release those. So let's say that that's the way your implementation works, and you want to make sure that all the negotiation and setup is done before you go and launch your kernel, because you don't know if the MPI implementation is going to, or better yet, I mean, it's just going to give you better performance to do it in that way. Is there some way that the user can try to nudge this along to you see what I'm saying? For not necessarily from the application behavior point of view, but from the performance tuning point of view?
So, I mean, one way that you could do that, I've thought a similar thing. One way that you could do that is that you could always in your application, you can, because it's a persistent operation, you can restart it after it's completed, right? And if you've done a start after you've already done a test or a wait on it with a completion, you know that the initialization is complete. And so you could theoretically, if you wanted to, hook up both sides of the buffer, right? Call P-ready on it if you had to for the entire buffer. And if that completes, you know it's initialized. The problem with that is it's extra overhead over the wire. You absolutely need to know it. But the tuning cases for actually knowing about this initialization seem to be minuscule. I mean, you could also do if you wanted to reduce the overheads on it, say you had a huge buffer that you were doing a partition call on, you could do the send init, receive init on that, and then you could set up another one after it that was a p-send, p-receive with a 0 size in a message, and you could test on that one, and when that's complete, it means the initialization's done, which means your previous initialization was also done. It's a little hacky, but it'd probably be a lot less than if you had a super huge buffer that you'd actually take some overhead from moving 128 megs or something like that over the wire just to make sure that your buffer was up and running. A 0 byte one is literally just doing a second handshake afterwards. It's probably fairly low overhead. I can also imagine that you could, in your MPI implementation inside of a request, very easily create a section of the state machine on that request state that could return this data to you if you really wanted to. But I don't want to try to define that our request is at a certain stage. Like you could hide this in the completion, the overall request, right? You could understand that requests are multiple stages, but we didn't want to introduce that at this point. But you could introduce that and get this optimization for essentially for free. But having a second request for it seems like it's overly ambitious with regards to resources that you need for it.
Yeah, I put a link to the paper I mentioned in the chat window for folks who are interested. I mean, I think this is this implementation technique is one that would be interesting to use as kind of a as a check for the API to make sure that we would be able to implement something like this.
Okay. Let me take a look at this. This looks kind of familiar, but let me take a look at this again.
Yeah, so the paper is GPU-triggered networking for intra-kernel communications. And basically the idea is that before you launch your kernel on the GPU, you set up a bunch of pending communication operations with the NIC that, the GPU may not be able to fully, issue commands, back and forth between the NIC, but it can release one of these operations that's been pre-posted. And so in order for that to work, you need to pre-post the operations before you launch your GPU kernel. And with the API definition right now, I guess it's hard for a user to figure out if they've been posted before they launch their kernel, and it's hard for the MPI implementation to figure out if the user's planning to use the API in this way. Or I suppose where the implementation might block to try and get this work done before the user launches their kernel.
Yeah, like I said, I think there are current ways around it that you could still do this with the API. That you could know this before you launched, for instance, a GPU kernel. But I think it's possible to do in the existing case, but it doesn't necessarily mean that it's super performant to do. Let's put it that way. So I guess my question out of this would be how often this is a use case. And like I said too, this can also be so even if we decided to go with the current single request model, we could still create a new call to ask about the init off of an existing persistent communication request. Sort of probe inside a request and find out what state it's in the future as well, if this is required to be sort of a super high performance path as well. I don't really know how often this is going to happen with CPUs.
Well, I mean, you could check with the authors on the paper and see what they're able to say. But I mean, I think that this type of communication model is something that will get used.
Okay, yeah. Let me talk to Khaled about it because as soon as he gets back from vacation.
Cool.
Well, thanks. Okay, I think we're out of time, Wesley.
Thank you for being punctual. All right, so the recording will be posted later this afternoon. We have another call next week, although I will not be there, discussing big count stuff that I assume Jeff Squires and co will be hosting. So thanks for coming, everybody, and see you sometime.
Yeah, thanks everybody. Thanks Wesley. Thanks Ryan. Bye everybody.
Thanks everyone. Bye bye.
Thank you. Thank